Everybody, Mr. Boyd. I'm going to do my best to try to make this video for you. We're going to go over these chapters one at a time. I'm going to extend your due dates. It's all going to be great. But just trying my hand at teaching the statistics through this online medium. Let's see how it goes. Let's get into chapter 4, section 1. This is from your Statistics Informed Decisions Using Data, 5th edition by Michael Sullivan III textbook. So we're going to draw and interpret scatter diagrams, describe the properties of linear correlation coefficient, you know that is the R value, compute and interpret the linear correlation coefficient, determine whether a linear relation exists between two variables, and explain the difference between correlation and causation. All of these things you did in Algebra 1, but let's review it anyway. So there are two different variables. There's the response variable, and then there's the explanatory or predictor variable. I'm going to go ahead and use the explanatory variable. So the explanatory or predictor variable comes first, obviously, because the predictor variable predicts something that's going to happen. The response is what happens as a result of that predictor variable. A scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. All this says is we're going to make a scatter plot using two columns of data. Usually the one on the left is going to be your explanatory variable and goes on the x-axis, and the response variable goes on the y-axis. So let's just take a look at some data here. The data on the right shows the depth at which drilling begins. We're going to be drilling rock. And then it says, how long does it take to drill 5 feet from where you begin drilling? So if, let's see, the researchers want to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which drilling begins is the explanatory variable. That's where we start. And they want to know, how does the depth that they begin at affect the time, I'm sorry, not the time, but the time it takes in minutes to drill 5 feet from where they started. And here is the table of values. If you take those, put them into Desmos, you make an X column and a Y column, and you do that. If you haven't seen it before, this is how you do it. You pull up desmos.com/calculator, you push the plus button right here, make a table, and then you enter in your values. Okay, so I've entered the data into my table, but I can't see my points. And the reason is I don't have this set to scale. The X values look like they're starting at like -6 and they're going up to 12. The Y values are going from -4 to 8. So I need to change the settings. I go up here to Graph Settings, and I'm going to change the X value. So here's X. What two values should it be between? Well, if you come over to your table, we start at 35 and end at 190. And I usually want to see the x-axis. So I'm going to start that at like -10. And I'm going to go up to 200. And that should give me all my points, as long as my y values are legitimate. And I'm going from 5.88 to 7.9. So maybe I want to stretch those out a little bit more because they look kind of horizontal. I might want to change the y values a little bit. The lowest is 5.88. Maybe I put 5.5. And the y values go up to 7.9. I'll just say 8.5. And in doing that, I can see the points a little bit better, that it looks like they're making an uphill climb. So maybe that'll be important in a moment. On this slide, you can see that it matches what we have on our Desmos app. The points are in about the same position. Their scale might be a little bit different. They go from a little bit less than 6 to a tiny little bit more than 8, and they go 0 to 200. So it's about the same. There are different kinds of relations we're going to be looking at. And all of them, the explanatory variable goes on the x-axis, the response variable goes on the y-axis. If you're looking at the data and it looks like it's kind of forms mostly aligned. It's kind of, points are kind of close to being going either up, going this other way, either going uphill or going downhill. Then that might be a linear relationship, and we can analyze that by doing some mathematics. If you look at that's letters A and B, you can see that if you make a line of best fit, those points are going to be really close to that line. Now this isn't necessarily a line of best fit. You might have learned this back in middle school as a trend line. There is only one line of best fit, and that is performed using mathematical calculation. You can't just draw any old line and call it good. So, but regardless, you can see that these two situations, A and B, they are linear in nature. If you look at letter C, that's obviously not linear in nature. It looks more quadratic in nature. So we might perform a quadratic regression on the data that produced these points for this scatter plot in order to find a quadratic regression equation that we could then analyze and extrapolate future data based on that function. Letter D is also nonlinear. In fact, it looks rather cubic, wouldn't you say? So that's nonlinear. And finally, letter C, those points just kind of look scattered all over the place. They don't look linear at all. Now with all of these, with A, B, C, D, and E, with all of them, we can perform a linear regression and try to find a line of best fit and just look to see how it looks. And then we can also calculate what's called the correlation coefficient. That's what's coming up next, and using that correlation coefficient, you can make a determination as to whether or not the data that you are looking at is indeed linear. It's as simple as doing some calculations, getting a value, comparing it to a table of values, and as long as the value you have is more than what the table says you need to have, then you have a linear situation. Two variables that are linear related, you need to know that they are linear related first. That we say they are positively associated when above average values, blah, blah, blah. Here's essentially what it means. Positively associated means that as x increases, y increases for whatever your x and y variables are. That's all that means. Negatively associated means that as x increases, as I'm going to the right on x, the y values decrease. So it would look like this from left to right. As x increases, y decreases. So x and y go in opposite directions when they're negatively associated, and x and y both go in the same direction. Either they both go up at the same time, or they both go down at the same time when they are positively associated. Okay, so the linear correlation coefficient, also known as the Pearson product momentum correlation coefficient, we're not going to call that. We're going to use the word linear correlation coefficient, is the measure of strength and direction of the linear relation between two quantitative variables. We use the letter rho, it looks like a lowercase p, to represent the population correlation coefficient, and the lowercase r to represent the sample correlation coefficient. In this one, we are analyzing the sample correlation coefficient, so you don't need to worry about the entire population, just a sample of data. Here is the formula. It looks kind of messy, but I'm going to show you how to use an Excel spreadsheet to calculate this. Now, once you've done it on a table or two and you're confident that you've used it correctly, then you don't need to do this anymore. You don't need to do it every single time. If you have a graphing calculator, or even you want to just type it into Desmos, it'll calculate the R value for you, and that will be fine for your purposes. All right, so let's get into what all of these things say here. X sub I means the ith element in the X table. So here's the X table, here's the Y table. Maybe these X values are 1, 2, 3, 7, 8, and 12. Well, then what is X sub 4? It's just the fourth element. So 1, 2, 3, 4. X sub 4 would be 7. That's all that means. X bar x bar right here is the mean of all the x values. So if you took all of those, if you took all of these x values, added them together, and then divide by 6, because that's how many items there are, that would be what your x bar is. And you would do something similar for y sub I and y bar. You'd calculate the mean of the y column. And that's super easy to do in Desmos. Why is that thing not erasing? Well, that's not my favorite thing in the world. I don't know what that was. So let's just keep going. All right. So you make a table. You have a table, and you calculate all of these different things. All right, let's try this again. Let's see. There we go. My system's not liking me tonight. All right, so what you're going to do is for every single value of x, you are going to take it and subtract the average of all the x values, and that's going to give you a result. Whatever that number is, you're going to divide it by the sample standard deviation, which you can calculate. I'm not going to make you calculate that out by hand. I'm going to show you a little trick in Excel. You can also do it in Desmos, but I'm going to teach you Excel to calculate that. So you're going to take every x value, divide it by the mean, and then divide by the sample standard deviation of x. That is going to be a value that you then multiply by doing the same thing with the y value. So whatever the x and y value ordered pair is, the x value goes here and the y value goes down here. Again, substituting y bar and s sub y. After you multiply that together, you're going to get some value as a result. Multiplying that together, whatever that first ordered pair gives you for this calculation is one value. Now, this symbol right here is sigma. Sigma means summation. So that means you're going to be adding other values together. And you're going to add together however many values there are, which should equal n. N just means the number of individuals in your sample, the number of ordered pairs, the number of rows in your table. Once you've added all those things up, you get some big grand total that you add up. You just divide it by n minus 1. So if there were 10 rows in your table, you divide by 9. So you should know the R value is always between -1 and 1. It could equal -1 or it could equal 1. If R does equal +1, that is a perfect positive linear relation. That just means that the points on your graph are all points that are perfectly on an uphill line. That's what that means. If R is equal to -1, what that means is that all of your points are means all of your points are on the same downhill line. So for something like this, R would equal exactly -1 if those points were perfectly on that line. If the line looks like it's going uphill, then R is going to be a positive number, but it's not necessarily going to be 1. So if you have points that look kind of like this, those points are clustered pretty well together. If I ask the computer program to give me a line of best fit and a R value, a correlation coefficient, it would probably be very close to 1. That R value might be 0.998, something like that. Who knows? Same thing if it goes downhill. The closer the points are together, the stronger the evidence is for that negative association, and the closer the R value will be to -1. So maybe -0.972 or something like that. If the R value is close to 0, then there is little or no evidence of a linear relation. So the R value only has to do with linear relations. If you want to show relationships that are quadratic in nature or cubic in nature, then you look for what's called an R-squared value, but that's not part of this lesson. R close to 0 doesn't imply no relation, just no linear relation. All right, so if you've got, for example, points that look quadratic in nature like that, they look parabolic. If I ask for a line of best fit and an R value, then my computer program or calculator might give me a line that looks like that, which those points don't really line up with that curve. The points on that curve, curvy shape, don't really line up with that line very well. So the R value is going to be low. It might be positive, it might be negative, depending on how that line is drawn. Maybe that line gets drawn downhill for all we know. But either way, it's not going to be a very strong R value. It's going to be closer to 0. So that doesn't mean there's no relation. It's just no linear relation. If those points look parabolic, then I bet there's a parabolic function that will map it pretty well. The linear correlation coefficient is a unitless measure, so it's not inches or grams or anything like that. It's just a number. There's no units to it at all. The units of x and y don't play any role into it. There's no miles per hour or anything. It's not resistant. If you add another point that is far away from the others, then that R value will change dramatically by the addition of that new individual value. So here's some examples. Part number 1, or part A, linear relation, R equals 1 because all of those points are on the same uphill line. On B, the points are uphill and they're very close together. So that's a strong positive linear relation. And R might be about 0.9 or more. On C, those points are getting a little more scattered, but it still looks like they're going uphill. If you performed a linear regression, I bet you'd get a point or a line of best fit, kind of like this blue line. R value would be a lot lower, it'd be closer to 0, like 0.4. If all of your points go downhill and they're all perfectly on the same line, then the R value is -1. So similarly, if you've got points going downhill, just if they look like they're very clustered together, it's going to be close to -1, like -0.9. These points are a little more scattered, so -0.4. On G, these points are just kind of all over the place. They're just kind of all over the place. So the R value is going to be very close to 0. And again, on H, you can see that looks parabolic in nature. So R, what is R? I don't know. It's probably going to be, they'll probably give you a line something like that. But R is going to be close to 0 because it's not a linear graph. So look at this situation. What do you think the R values would be here? Looks like there might be a line that goes through something like that. If I were to predict, I'd say the R values are about 0.5 or maybe greater than that. There's no way to tell just by looking at the points. You really just have to graph or do the math behind them. Okay, so here's how I'm going to teach you the Excel stuff. Okay, so here's that table with all that data. Let's go over to Excel. Okay, so what I want you to do is set your screen up to look like mine. Set your screen up to look like mine. You have an N column with numbers 1 through 12. That just means the first item, second item, third item. That's all we're saying. We're not going to use these numbers 1 through 12 other than to just know that there are 12 items. N equals 12 because there are 12 ordered pairs. Each ordered pair is an X value and a Y value right next to each other. So what is the value of Y sub 8? Well, Y sub 8, you'd go to the Y column and go down to where N is 8. So Y sub 8 is 7.97, right? Okay, so in column D, you're going to put at the top X bar. Column E, standard deviation of X. Column F is Y bar. Column G is standard deviation, sample standard deviation of the Y values. And this comes from the formula. Remember, we're taking every X value in the table. So like 35, 50, 75. We're taking those x values and we're going to subtract the x bar. We're going to subtract the mean. And then after we do that, we're going to divide by the sample standard deviation, SX. And I'm going to show you where we're going to calculate those. We're going to do the same thing with the y values, and then we're going to multiply those two things together, and that'll be the product. Once we get all those products, we're going to add them together, and we're going to put them in this cell, J15. To the left of that, it says sum. That just means the sum of all those products. And then the last step, the R value, is just the sum divided by n minus 1. So let's calculate the mean over here. What is the mean of this table? Well, you're going to type average, and then parentheses, and then just highlight. Oh, excuse me. I apologize. You got to type equals average, open parentheses, highlight, or click and then drag to highlight the entire column of values, close parentheses, hit enter. Now you're going to do the same thing with the y values right here. Oh, and by the way, you can double click on any of these bars right here to widen them if you need it widened. So equals average, parentheses, highlight them all, close it, and hit enter. And that's the average for that one. Again, you can double click that bar and it'll widen it to give you more decimal places. Now, one other thing you can do is highlight a cell that you've already done a similar calculation with, that you want the same calculation done in the next cell over. So now that I've got 126.25 highlighted, I'm going to hold shift. I'm going to hold shift and then push the right arrow key, and that highlights them both. And then hold Control and R, R meaning to the right. It's going to copy that formula over to the right. And there you see I get the same value, 6.985. Underneath 126.25, I'm going to calculate the standard deviation of the values in the x column. So just type stdev, you got to do equals stdev, open parentheses, highlight the x values. Remember, we're not using the n column. You can ignore that. Close parentheses, hit enter. Again, double click the row if you want to get more values. Underneath, we want to fill in this. So in cell C16, you can either type in the formula again and highlight all the cells, or just highlight the 52 value, shift right to highlight both cells, and do Control R to copy to the right. One more thing you can do if you want to copy a group of cells to the right, then you can highlight both of them. In this case, hold shift right and it'll double the length of that rectangle, and then do Control R and it will just take both of those those formulas, and it'll copy them over to the next cell. And either way, however you choose to do it, you should have now x bar, standard deviation of x, that's SX, y bar, and SY. Now what I'm going to do is copy these values one at a time and put them in the second row. Put them in these values here, in these cells here. So right click and copy, or Control C. Now here's the tricky part. Your temptation might be to do Control V, or to go up to home or something and paste. Resist that urge. Instead, right click and see here where it says 1, 2, 3. If you click that, it will only paste the value. If you do Control V, it doesn't paste the value, it pastes the whole formula. You want just that number. So click that. For standard deviation of x, again, you can copy that. You can right click and do copy, or you can do Control C there. But in box E2, right click and do paste value. The mean for y, right click, paste value. Standard deviation of the y values, right click, paste value. It's important that you don't just copy down the formula, because because what we're going to do is copy all of these values down. And those values will look very different if you did Control V. So if you did Control V, delete it and start over and just paste the values. Highlight all 4 cells by highlighting the first one and holding Shift and hitting the right arrow key 3 times. Another way is to just click and drag to highlight those 4 cells. Then hold Shift and push the down arrow key, or again, you can just highlight the whole 4 columns all the way down through row 12. Now we want to copy those cells down. We want to copy the exact values down. Not, every single value is going to be the same. So in each column, do Control D. Control D will copy everything down. Perfect. Now we start doing the actual big time calculations. So I need a formula. Equals parentheses, close parentheses, divided by. Now we'll do the parentheses last. What goes under the fraction bar? It was SX. Well, the standard deviation of the X values was this cell right here, E2. So just click that cell. I'm having you do this instead of just typing in this spot, 52.229, because typing that number into that spot, you're rounding. And then if you do more calculations with a rounded number, you're going to get numbers that will be off. You'll get rounding error if you round too many times. So the best way to do it is to just copy the value that's in that cell, and that value was copied from cell B16. The reason we can't just use B16, I'll show you. If I do that, let's just say I typed in just B16. Great. If I do Control D right now, it's not going to, what it's going to do is not just copy that value down. What it does is it copies down that value and the 11 values underneath it and moves them up here. That's not what we want. I want to have 52.228 in every value. So if you say equals this 52.229, whatever, it's rounded, and then do the Control D thing, it'll copy them all down. That's exactly what we want. So let's start this again. Equals parentheses, parentheses, divided by. In the denominator, put 52.229, but click this cell. And in parentheses, you need an X value minus the mean. Well, the X value is 35, that's in B2, minus the mean. That's X bar, and that was 126.25, which is in D2. Hit enter, and that gives you one of those sets of parentheses. Remember, there was one for X and one for Y. To get the Y values, you do the same thing, equals parentheses, parentheses, divided by. In the denominator, you're putting the standard deviation of the Y values. In the parentheses, you choose the Y value, 5.88, and you divide by Y bar, which is about 6.99. Oh, excuse me. 5.88 minus Y bar was 6.99. There we go, and that's a Y value. Now we're going to multiply these two cells together. So put equals, click the X value, and then do an asterisk. It's above the number 8. So Shift 8. And then click I2. We're going to multiply those two cells together. That's one of our products. Now we just need 11 more and we can add them together. It's very easy. Highlight all of those. Highlight the entire column all the way down. Control D. There you go. Now this is the column of values that I'm most interested in. These are my products. I've got to add those products together. So equals sum of all of these values. And now in this cell, we got to take what was in the cell above it, the sum, and divide it by n minus 1. So J15 is the sum of all those products, and we're going to divide by n minus 1. Well, what was my n? There were 12 ordered pairs. So it's 12 minus 1, or you could just put 11 in the denominator. That is what your R value is. That is the thing that we needed. Now, if you leave this formula up, or if you leave this table up, the only values you'll need to change are these that I'm highlighting in yellow. If you have a table, another table with 12 values, all you have to do is change out those yellow columns with 12 new ordered pairs, and the value in green will update automatically for you. If I needed to extend this, I could add more rows. I could right click and do insert. Right click and do insert. Now, I might need to change some calculations. Like this mean for X and this mean for Y, it only goes through the 13th row, C13 and B13. If I wanted it to go farther, I would need to, like if I added some, if I added another ordered pair, let's say 210 and 235, and let's say this is 8.2 and 8.9, something like that. Yeah. Then I would need to change the values for mean and standard deviation. I would need to I would actually need to change these 4 values right here as well after I calculated them. But upon doing that, everything else should just copy down. So if I put a 4 right here, no, that didn't work. So you would still need to copy it all down. So it's not quite as easy as it looks, but you get the idea. This is how you would create it. Once you get good at it, it's not that hard. So look at this. Here, let me delete these 2 rows so we don't get confused. Look at our R value. It is 0.7728. That's about 0.773 to 3 decimal places. Let's go back to the PowerPoint slide. Okay, so they did it just about what we did. They calculated the x sub I minus x bar over s of x. They did that here. They did the same thing for the y value. Again, this is just this ordered pair. You multiply those together to get a product. You do that for every single row all the way down, every ordered pair, to get all these sums. And then you just add them all up to get a total. When you add these particular values up, you get a total of 8.501. That's the summation of all the products. And then when you take 8.501 and divide it by 12 minus 1, or which is 1 less than the number of ordered pairs, you get 0.773. And that's exactly what we got in the Excel spreadsheet. Now let me show you how to use Desmos. If you've done this a couple times and you've calculated an R value by hand, good for you. I don't want you to feel like you have to do it all the time. I'm going to show you how to find the R value in Desmos very, very quick. Okay, so on Desmos, you click the plus button for add an item right here, and you make a table. And then in that table, you type in your ordered pairs. Well, I've already done that. Done that right up here, got a table. And you can see the points. Now I'm going to type in a linear regression equation. Normally a linear function is y equals mx plus b, right? Slope-intercept form. We're just going to change 3 things. First of all, it's not just x. It was x1 from that table. So put a 1 right after the x. Just push the 1 button, and there it is. For the y, you put y1 because that's the column. Notice all the points disappear. And I'm not sure exactly why they disappear, but I know that there's one more change that we make. If we do it, it will give us the line of best fit and the R value. Erase the equal sign and put a tilde, like the thing above the ñ letter in Spanish. It is right next to the 1 key, So hit on the left side, hit shift and push that button. There you go. That's the line of best fit. That line, there is no finer line. You could maneuver it however you want. Mathematically, any other line is imperfect. This is the perfect line. Notice down over here, it gives you the R value. What does it say? 0.7728. Exactly what we got with Excel. Furthermore, it gives you an M and a B. That tells you the equation for the line of best fit. So y equals, so what is M? If you're not sure what M is, you can just, I mean it's right there, but it's rounded to 6 decimal places. If I just type M, it gives it to me in like 12 decimal places. Same with B. If you just type B, it gives it to you in more decimal places. And then you can just type in the equation, y equals mx plus b. And it graphs it right on top of the line of best fit. You can call it f of x equals mx plus b. That's even better. Here's why that's even better. What if I want to make a prediction? What if I want to say, well, what if I'm going to start drilling at 300 feet down? That's nowhere near any of the values in my x column. I want this to be 300. But I don't know what the coordinate will be for y, because that data has not been gathered. So I just extrapolate by typing in f of 300. About how long will it take to go down 5 feet? 8.99 seconds. So or minutes. Was it minutes or seconds? Either way, whatever the units were, it was 8.99. I think it was minutes. So it'll take about 9 minutes to dig 5 feet if we start 300 feet underground. That's what this line of best fit tells me. And if I graph a point called A, and I say x is 300, comma, what is f of 300? That's the y value. You notice that that point is exactly on the line. And is it going to be a little bit above the line or a little bit below? Probably. It's probably not going to be exactly 8.993, but this gives us a rough estimate that we can work from. Okay, so how do we test whether or not this is actually a linear relationship? That R value wasn't that high. You know, it wasn't anywhere near 0.9. It was 0.773. So how do we determine if this is actually a linear relation? Well, you do exactly what we just did. You calculate the correlation coefficient. We just did that and said R is about equal to 0.773. Then you take the absolute value of it. You just want the positive. So the absolute value of R would be about still positive 0.773. If it's negative, just kick off the negative. Next, find the critical value. The critical value is going to be something given to you. On your homework, if you've already done it, then you know. If you haven't done it yet, you'll notice that there's a table that they offer you. You definitely need to look at that. So again, the absolute value of our R is about equal to 0.773. Let's look at the table. Well, what was our N? How many ordered pairs did we have? We had 12. The critical value for N ordered pairs is 0.576. So the critical value is 0.576. Is it the case that the absolute value of R is greater than the critical value? If that's true, then the relationship is linear. So that is the case, isn't it? Our absolute value for R was more than the critical value with 12 ordered pairs, so we say that a linear relationship exists. And as you can see, they came to the same conclusion. Since 0.773 is more than 0.576, there is a linear relation. Okay, so according to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. So the correlation between those two things, the percentage of people in the United States that are women that have a bachelor's degree, and the percentage of births that are given to unmarried mothers. They calculated those for every year since 1990. And then they got an R value of 0.94. So what is the absolute value of that? It's 0.940. And then we would need to look for a critical value if we want to determine if it was linear. Now notice it says since 1990, so I don't know how many years, I don't know when this was made. I mean, it started in 2010, it was recopyrighted in 2013, 2017, so I don't know how many years after that. It's been 30, does that mean N is 30? Not necessarily, it depends on the sample data. But before we get into that, let's look at the question. The question says, since the value is 9.40, does that mean that a higher percentage of females with bachelor's degrees causes a higher percentage of births in unmarried mothers? Does one cause the other? Of course not. There is a correlation between both because both percentages have been increasing. More women have been getting bachelor's degrees, and more women have been having births while being unmarried. More women are getting more bachelor's degrees because that's the changing workforce, and more women are having children without being married because of the changing familial dynamics that have happened over time. So but we still notice that they're increasing together, and a pretty high correlation, 0.94. Just because there is a high correlation between two sets of data doesn't mean one causes the other or vice versa. It doesn't mean that one is necessarily the response variable and the other the explanatory variable, either direction. There could be a third variable that is unknown that affects both of them. It's like when they say that more ice cream cones and more murders happen at the same time. More people are murdered as more ice cream cones are being sold. Does that mean people eating ice cream cones are causing people to get murdered out there? I had like a 10-minute discussion with students. They're trying to convince each other that they know what they're talking about. Instead, they didn't just slow down and think, wait a minute. Okay, they can't go together. One can't affect the other. That doesn't make sense. There must be some other reason. I didn't get a single kid that said that. It was pretty wild. These are ninth graders, though. You remember ninth grade. So what we're talking about is a lurking variable. With the ice cream and the murders, the lurking variable is obviously the heat. The hotter it is, the angrier people get, and the more likely they are to murder somebody, I guess. And in this case, oh, yeah, so there you go. The ice cream sales and crime rates. Yeah, very high correlation. No, the temperature. So it's a very common common reason. So what do you think would be the lurking variable for more women with bachelor's degrees and more babies born out of wedlock? Think about that. Pause it if you need to and think about it, because I think I have an idea. Okay, I think the reason is just society's becoming more liberal. In more conservative eras, back in like the 40s and the 50s, women were expected to get married, stay home, be a housewife, clean the house, take care of the kids when they come home, help them with their homework, have dinner ready, all that kind of stuff. But in the 60s, in the 1960s, women's liberation was a really big thing. Late 60s, early 70s, and it continued all the way through the 80s and beyond, really. Women started deciding for themselves what kind of lives they wanted to have. So that's why more women have bachelor's degrees and more women have untraditional families. Okay, so here's a table. The number of colas different people have had per week and their bone mineral density. So we talk to one person and say, how many Cokes did you have this week? Okay, 0. Let's measure your bone mineral density with this bone mineral density test. So 0.893 grams per cubic centimeter, or yeah, 0.893 is the bone density from the neck, the femoral neck bone, I guess, from a sample of 15 women. The data were collected through a prospective cohort study. All right, so here is a table of the scatter points. They look rather linear, looks something like that. We could, of course, get a line of best fit. We could perform a linear regression to get that line of best fit, and also calculate the R value. Well, they've already calculated the R value for us here. It's a negative 0.86, and you can see why it's negative, because the points obviously decrease. The more sodas a person has, it looks like the lower their bone mineral density is going to be. But we need to determine whether or not it is truly a linear relationship. So let's take that R value, which is negative 0.86, or 806, and take the absolute value of it. Well, that's 0.806. Now we need the critical value. Well, N was 15. There were 15 women. So if I go back to this table here on this slide, it doesn't have 15. I don't know what that value is. So you're going to have to go into your textbook to find it. It's in Table 2 of Appendix A. It's in the back of the book somewhere. And it will tell you there that the critical value for 15 elements, or 15 ordered pairs, is going to be 0.514. Is our absolute value greater than the critical value? Yes, it is. Because the absolute value is greater than the critical value, we can conclude that there is a negative linear relationship between the number of colas consumed and bone mineral density. Can the authors then conclude that an increase in colas consumed causes the decrease in bone mineral density? Probably not. There might be other lurking variables. All we know is that they are related in some way. There may be a third variable that you have to figure out. So some lurking variables could be body mass index, a person's height, maybe the taller they are, that affects their bone mineral density. If you smoke, all kinds of bad things happen to your body. If you drink too much, bad things happen to your body. The more calcium you take in, the higher your bone mineral density is. And any kind of physical activity could cause a change in it. So the authors, whenever they put out a study like this, they are very careful not to say that one causes the other. They don't say that more colas decreases bone mineral density, or that by actually it wouldn't work the other way, would it? Oh, by increasing your bone mineral density, you start to drink fewer drinks, so fewer soft drinks. That doesn't make sense. Obviously, drinking colas would be the explanatory variable, if there weren't some other lurking variable, which there probably is. Okay, so that is the end of that. We are done with 4.1. Stay tuned for 4.2. Please be sure to like this video and smash that subscribe button. I'm just kidding. I'm kidding. I don't care. I really don't care if you smash the subscribe button. What am I, a YouTuber? I'm not a YouTuber. Or I look like a YouTuber? I'm not a YouTuber. All right. See you later in 4.2.